Welcome to Arxflix. Today, we're exploring a groundbreaking paper titled Scalable Adaptive Computation for Iterative Generation. This research introduces recurrent interface networks, or RINs, a novel architecture designed to efficiently generate high-dimensional data like images and videos. Let's dive into the key aspects of this paper. Traditional neural network architectures like convolutional neural networks and transformers apply computation uniformly across all data points. In real-world scenarios, data is often redundant and inconsistently structured. This uniform allocation of resources leads to inefficiencies, especially when dealing with high-dimensional data. The problem becomes more pronounced with tasks like image and video generation, where certain regions, like static backgrounds, don't need as much computation. Recurrent interface networks, or RINs, aim to tackle this inefficiency. In this model, most computation is focused on a set of latent tokens using global self-attention, while interface tokens handle the data interaction using cross-attention. RINs partition hidden units into interface Z and latents Z. Interface units grow linearly with input size and are locally connected to the data, while the latents form a compact representation where the bulk of computation occurs. The RIN architecture processes data through a stack of blocks that read, compute, and write information, alternating between local and global processing. Here's a breakdown of the RIN computation graph. Information flows from interface tokens to latents via cross-attention, and vice versa, accumulating context iteratively. A key application of RINs is in iterative generation tasks like diffusion models. These models progressively refine data from noise to a structured output. RINs leverage this process by warm starting the latents, using previous iterations' latents to build context, leading to a deeper and more efficient network. The process starts by applying a series of state transitions to map noise to the data. RINs use latent self-conditioning to maintain context across iterations, ensuring more expressive routing and efficient computation. RINs exhibit state-of-the-art performance in both image and video generation tasks, surpassing traditional unit architectures. What's more, they do this while being up to 10 times more efficient in terms of floating-point operations. RINs dynamically allocate computation where it's needed the most. The read attention maps reveal that the model focuses on complex regions, ignoring redundant or static areas. The paper presents several significant contributions. First, it introduces RINs as a domain-agnostic architecture capable of adaptive computation. Second, it identifies the advantages of recurrent computation settings and latent self-conditioning. Finally, it demonstrates impressive performance gains over existing diffusion models for image and video generation. RINs represent a significant advancement in scalable and adaptive computation for iterative generation tasks. By focusing computational efforts on the most informative parts of the data, RINs offer a more efficient and effective solution for generating high-dimensional outputs like images and videos. This architecture paves the way for more complex and scalable generative models in the future. Thanks for watching today's episode of Arxflix. If you found this breakdown helpful, don't forget to like, subscribe, and hit the bell icon for more deep dives into the latest in AI research. See you next time. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.